Okay, let's get started. So today is the second day on data. Last time we talked about how data doesn't really just fall from the sky. You actually have to think about where it comes from. So in general, the internet consists of live services. The data on those services have to be either dumped or crawled. And then there's an additional step where you have to process the data. And we also talked about various societal considerations, terms of service, copyright. You have to either get a license or appeal to fair use. So there's a lot of complexity that goes into data. So today we're going to look more at the data pipeline, from transforming the data, filtering the data, deduplication, and mixing. And then we're going to top it off by talking a bit about post-training data, in particular how folks are using synthetic data these days. So the first part is going to be mostly about pre-training. That's what you should have in mind. So we talked a little bit about data transformation already, but just as a kind of reminder, so raw data doesn't come as text, even as if you've scraped something. If you ever look at inside Common Crawl, it's not text. It's either HTML. Sometimes it could be PDFs or directories in the case of GitHub. So most of the attention on transforming data is dealing with HTML because most of the web is in HTML. And for this processing, there's a lot of this is fairly heuristic. There's removing of boilerplate, like navigation and ads, and extracting content, which is like the main part of the page. And there's some subtleties around what constitutes content. Usually you get rid of the footers and headers and maybe menus and those things, and you try to extract the content. But you could imagine in cases where some of the navigation elements might be helpful to learn what web pages look like. So what is content and what is not content is not always clear. And then what do you do about images and tables are in web pages? So inherently, this is a lossy process because you need to linearize HTML, which at least is either hierarchical or visual, if you think about the rendered output, and to a sequence of tokens. In particular, tables are a bit tricky to deal with. Simple tables you can render using Markdown. But if you have nested tables, then that becomes quite challenging. You have to give up at some point or approximate at some point. So typically, HTML to text processing is rule-based. And the reason for this is that rule-based processors are very fast. And also, you're not trying to do too much here. You don't need too much intelligence, so rule-based generally works. Now, I think there could be a case for model-based interventions at this point. They have to be very fast, and they have to do something more intelligent. But if you ever look at data, you'll notice there are imperfections in the data just because any rule-based processing is going to be have some failure rate. As we showed last time, the accuracy does matter depending on which tool you choose. If you use Brasilia parse or Traflatura, then it's I guess Brasilia parse on these extended DCLM evals works better than the others. I'll talk also briefly about PDFs. So there's this Hugging Face work which released a data set called Find PDFs. So PDF files, if you ever open them up, not in a PDF reader, looks kind of like this. And this needs to get kind of rendered. So PDFs can be found on, just like web pages, on the internet. And Common Crawl does have some PDFs. Generally, Common Crawl focuses on text, but sometimes if you're just given a URL, you might not even know before you fetch it whether it's a PDF or not, if it doesn't have the extension. There's a lot, if you read this blog post, there's a lot of details which I'll spare you of. For example, one thing is that many of the PDFs that are in Common Crawl are truncated because PDFs are big. So then that demands that recrawling is necessary. And then there's a question, once you have the PDF file, how do you actually convert it to text? And some PDFs might be just scans as well, right? So they're essentially images. So there's a bunch of tools that this paper tried out, but mostly this kind of involves running OCR using a VLM. And this obviously can be much more expensive than what we were doing before with text. Fortunately, or unfortunately, the PDFs are a very small fraction of the whole internet, but they are very valuable because generally if you bother to make a PDF, that means you probably have something interesting to say as opposed to a web page. So the quality of a PDF average PDF is generally higher than for a HTML file. There's a lot of cleanup and filtering, and PDFs more so even than web pages, a lot of layout information is missing because in HTML you have various tags like H1 and P that gives you some semantic information. PDFs are by design all about layout, so you don't necessarily preserve the kind of the semantic structure. Okay, so there's a bunch of transformation that happens. At this point, you have text, but you're not done. You're far from done. So the next step is filtering. So I'm going to talk somewhat abstractly about what filtering is. Here's the sort of the building block. So suppose you have some target data that you want to get. This is usually a small amount of high quality data and lots of raw data. This is the fresh shipment of the tokens that you do transform from the previous step. And the goal is to find a subset of this raw data that is similar to target. So this is the general skeleton for filtering, and almost all kind of filtering falls into this schema. So filtering, there's many reasons you might want to filter. If you're training an English language model or a German language model, you might want to identify the language and filter things that don't match that language. The main reason for filtering is quality filtering. You want to find things that are high quality as opposed to low quality. You don't want just spam. You want encyclopedic information. And then another application is toxicity filtering. Of course, the internet has plenty of nasty content, and maybe you don't want to train your language model on that. Okay, so for a filtering algorithm, you want some generalization from the target data, right? Because you already have the target data. You don't want to just only get the target data. But you also want it to be extremely fast because you have to run it on the whole internet. So this could be 100 trillion tokens worth of data. So generally filtering is you end up with a very small fraction, single digits fraction of your entire data. Okay, so remember the general framework, given the target and raw, you're trying to find a subset. Okay, so the general scheme is that you estimate some sort of model based on R and T and derive a scoring function, and then you keep the examples in R based on their score. So typically there are two types of classifiers. One are generative models. So this is basically you have your target data. You can just estimate a model of that data. And remember, this has to be cheap, so probably you're not training a big language model. Generally, KNLM basically says, I'm going to train a 5-gram model. A more common thing, which I think we're mostly seeing these days, is just train a classifier. And the classifier says, I'm going to predict a positive label for examples that are in T, my target, and negative labels for things that are in raw, but not in T. So you basically, it looks like T are your positive examples, some random subset of R are your negative examples. Maybe you balance it, and then you train a classifier. And the tool that people generally use is fast text because it's fast, and it's just a linear classifier, bag of words. And then once you have this model, now for every new document, you can score it, and you set some appropriate threshold depending on your quality bar, and you keep the examples, sometimes stochastically, sometimes not. Okay, so this is very much a model-based filtering approach. Remember from the last lecture, there are many data sets from generally a few years ago that did not use model-based filtering because they wanted to not bias things too much. These days, I think basically everyone does some amount of model-based filtering because unless you are compute plentiful, in which case you probably don't need to do as much filtering. You can just train on everything. Most people are compute poor. You have to be very smart about how you're filtering. Otherwise, you're just wasting flops on kind of low-quality content. Okay, so let me talk through some instantiations of filtering. So remember I mentioned language identification. So the goal is just to find, given a piece of text, detect whether it's of a particular language. So Meta has trained these set of fast text language identification models, which often you can just use off the shelf. So it supports 176 different languages. It's been trained on a bunch of multilingual sites. So Wikipedia, remember, has a lot of languages. There's also translation sites and sites for different languages. So a language ID is generally a fairly easy problem compared to many other tasks that we're dealing with. So a simple classifier, if you look at a few words, you can tell that it's Spanish or Japanese. Now, there are subtleties because of code switching in text, and there's some dialects. So I wouldn't say it's like absolutely solved problem, but this is not really the bottleneck for training a good language model. Okay, and then you can so once you have your classifier, you just choose some threshold. This is generally fairly heuristic. So another thing you can do with filtering is that suppose you're looking for data of a certain type. So let's say you want to get really good at math. So you want to go and find a bunch of math data. So Open Math Text is this paper from 2023 where the goal is to curate a large corpus of math text. This pipeline consists of a few steps. So it's not training a single classifier. So first you use some rules to filter. Does it contain LaTeX commands? They also use CanLM, so this is a generative approach, and trained it on the proof pile, which is a known data set of math, and keep it if the perplexity is below some threshold. And then you also train a fast text classifier to predict whether it's mathematical writing or not. And there's two different thresholds. If it has LaTeX in it, then it's a higher bar. If it's it's a lower bar, but if it doesn't have LaTeX in it, it's a higher bar. And then as a result, they got 15 billion tokens, which they use to train models. And as a paper, they show that this more targeted curated data collection results in models that are better than math than models that were trained on 20 times much data, which were not filtered in this way. Okay, so the quality filtering, again, think about it as a tool. You can define quality however you want. There's no universal notion of quality. If you want define quality to be math, then you can go and get math and you get better at it. So GPT-3, I think I mentioned this last time, but just to put it in this framework. So positive examples are Wikipedia, web text. So these are pages that link out from high star Reddit posts, and some books. And negatives are generally sampled from the web. They train a linear classifier and keep documents if the linear classifier is scored highly enough. There's the first Llama paper. The positives were pages referenced by Wikipedia. not Wikipedia articles themselves. And it's this kind of same idea. So Phi1 from Microsoft is interestingly had, it also falls into this framework. So they started with the raw data is not already a Python subset of the stack, remember, which is this all code, and the prompt, they define a prompt which is determine its educational value, and then they use GPT-4 to classify a subset of R, 100K subset of the R, with this prompt and see if it's and the ones that are positive are kept and called the target. Right. So the target here is actually output of an expensive classifier. And then you train a cheaper classifier, in their case, a random forest, but you could have probably used fast text as well. And then you select data that is classified positive by this classifier. And they also show that using this data set, you do much better than if you're just using the raw data. So this performance goes up in fewer steps to a higher value. Okay, so toxicity kind of works the same way. There's this data set, Jigsaw toxic comments, where it came from this project where the goal is to help people have better discussions online. So here the data is the Wikipedia talk pages, which can, I guess, for controversial sites get quite heated. And this has been annotated with whether there are any toxic comments there. And you can similarly define positive and negative examples, and you can train a classifier on that. Okay, so now I think you have the tools or some examples and inspiration. You can identify a particular type of data that you want. You build a classifier for it, and then you can go filter Common Crawl for that. I want to talk about one subtlety here, which is that the notion of what you want for data is actually depends on what model you want to train. So in particular, it depends on the number of tokens you're training on. And so there's no optimal threshold. So before, when I looked at the classifier gives you a score, you can't say 0.9 and say that's the best, because it depends on what you want to do. Intuitively, if you are going to train for a longer period of time, then you can tolerate lower quality data. If you're training for shorter, then you want higher quality data in general. Okay, and of course, if you could wave a magic wand, if you're training for longer, you want more high quality data, but that's not an option. That you're given the data pool is what it is. So here's a kind of a preliminary experiment that Michael Ryan did. And so basically this plot shows for a 157 million parameter model, we're taking a very small pool, so 100 works, which is a tiny fraction of Common Crawl. And we're training for more over time. So let's take a look at the blue curve. So the blue curve is DCLM. And so the loss starts here, and then it comes down. And each of these lines is when you epoch over the data. So this is one epoch, and then the next blue is the second epoch, and so on and so forth. So there's not that much data. So eventually, you have to repeat your data. And the loss continues going down. Because the second time you look at the data, you're still learning things. And at some point, you start to overfit. Okay? Whereas if you look at Resilia parse, this is basically no filtering. So here, it's much worse in the beginning. But as you continue and continue, at some point, you also epoch, it starts to go down slower. So you kind of see this trend where high-quality data is better in this regime where you're not epoching. But once you get to lots and lots of tokens, high quality data is no longer that great. And of course, with high quality data, you wouldn't want to go into this regime because you're overfitting. You'll probably stop here. But even at this point, this is worse than if you had trained for longer using low quality data. Yeah.
Just a question about like the computing the metrics. This is actually not like totally about the graph, but like when you're like each of those dots correspond with one training run, right?
Yes.
Do you ever need to do like confidence intervals when you're doing these kind of pre-training experiments, or like is it kind of enough just to do it one time?
So the question is, each of these points is a single training run, and should you do it multiple times and get confidence intervals? Ideally, that would be good practice. Often you'll see in these papers that these are kind of scarce because each training run is fairly expensive. But in reality, when we have done these experiments, it's generally tends to be stable, I would say, at least for pre-training. Yeah. Yeah.
So you mentioned like training for longer and high quality data, as that's not like a combination that we're considering. But like if we are training with for longer on this high quality data, would it have diminishing returns compared to like training for longer with the lower quality data?
Yeah, so the question is, if you were able to get higher quality data and you train for longer, would it still have diminishing returns? Every data set is going to have diminishing returns eventually. That's finite. But it would probably be here. It would just like be down here and just keep on going down. Okay, great. Let's move on. So summary. Filtering is pretty critical for building a good model, especially when you're compute constrained, like most of us. Technically, if you have infinite compute, you don't need to filter, and you can train on everything, and it'll be a giant model. But realistically, everyone has to filter. So and the recipe here is figure out what good data looks like, and then you can train a classifier, and that will extrapolate to the rest of your model. And what good data looks like, you can either find it by saying, aha, there's this data set out there that I really like and I just want more of it. Or you can craft a prompt to a language model and then use that to construct, to do a sort of a preliminary filter of a large pool, and then use that good quality data to train a smaller classifier and extrapolate to everyone else. Okay, next I'm going to talk about deduplication. So at this point, we have filtered our data set, so we only have what we deem to be high quality data. But often data still has duplicates in it, and there's two types of duplicates. There's exact duplicates. So this happens when, for example, if you look at these mirror sites, the whole point of a mirror is that it's a duplicate. And sometimes the web crawler isn't smart enough to know that this mirror is exactly this mirror, so it just crawls many sites, and you'll get this exact same content. Also, when you fork a repo, that is also a duplicate. Even if you make changes, probably you're making changes to a few files, so 99% of that repo might be the same. So duplicate is abundant. And yeah, sometimes there's actually near duplicates, which are not mirrors or derivative, but they just happen to be same text differing by a few tokens. Usually, probably this came from a kind of a, it could be copying or came from a different common source. So here's some examples of near duplicates. So terms of service and licenses. So I guess the MIT license probably shows up on a lot of places, and so in many cases it is a exact copy, but only of that license, unless someone made a typo when they copied it. But the rest of the page that the license might be part of might be different. And we talked about how a lot of websites have the same headers and footers. Those are also duplicates. There's also cases where for whatever reason, there's this is from LM1B, so the 1 billion per benchmark. There's like these articles where you just have typographic differences. Like there's one version with a comma and one version without a comma. I don't really know why, but that happens. And sometimes you see these templates where this is like some probably low quality content where it's like essentially looks like an ad of some sort, and someone just templatized, replace Canada with USA. So if you train like on this data, but you are just training on different variations of this with different entities, this is going to be wasting your GPUs. There's more extreme cases, so this is why it's good to look at your data. So this audit of the C4 data set found this product description 61,000 times in the data set. And if you trace back, this is really bizarre. I don't know why. This is like some description of this gas mask. And this just showed up in this data set in Common Crawl 61,000 times. So yeah, the web is weird. So why deduplicate? So the first clear idea is clear because you want to train more efficiently. Deduplication reduces your data set size without really losing information because you're just removing duplicates. And it also has this benefit of avoiding memorization, which this paper talks about. For example, if you have some copyrighted content that's duplicated a lot, then if you train on it, then you'll memorize it, and also privacy concerns. But mostly, I think it's just to make sure that you're not wasting flops. Related to deduplication, there's also decontamination, which is arguably even more important and it's the same sort of deal, is that you want to make sure that your test set is not in your training set. Okay, so how do we dedupe? So here's the design space to think about. So first of all, what are the items that you're deduping? Do you do at the sentence level, the paragraph level, or the document level? How do you determine a match? Is it exact match? Is it existence of a common sub-item? Is it the fraction of common sub-items for near deduplication? And then once you found a duplicate between two pages, what do you do? Do you remove all the instances, or do you remove all but one? Okay, so and the key algorithmic challenge is that deduplication is fundamentally about comparing items to other items. And normally, if you're doing filtering, this is about an individual item. This item, is it good or not? And this can be parallelized. It can be, it's sort of linear time, which is good. And even in linear time, we're trying to make it fast by having rule-based or very small models. But deduplication, clearly you can't do the n-squared thing where you compare everything to everything. You need linear time algorithms to scale, especially at this web scale. So typically, the deduplication literature uses hash functions to get around this. So we'll develop some of these ideas. These are quite nice ideas from thanks to the algorithms community. So I think everyone knows what a hash function is. It takes some sort of value, like a string, and maps it into something like a string or an integer. And the hash value is much smaller than the item. Hash collisions are when two distinct items map to the same h. Okay? So when you look at hash functions, there are really fancy hash functions which are cryptographic in nature. These are collision resistance using cryptography and Bitcoin and things like that. And then there's these like faster ones which are used for hash tables where hash collisions aren't the end of the world. And so we'll be using these. Okay, so take a string and map it to some value. That's what hash functions do. Okay, so exact duplication is conceptually very simple. You take a string, you see if there's an exact match, and you remove all but one. Okay, so here you have a bunch of elements, and you hash them, and you dedupe. Okay, so this is And exact duplication is very nice. It's very clear what's happening, but this isn't really good enough for the messy web data because often you have these near duplicates. And one note is that there's many ways to have written this. This is written in a sort of like a bit of a map reduce style way, which makes it more easily parallelizable and scale. So C4, this paper from the T5 paper, which processed Common Crawl, did exact deduplication. The items they operate on were 3 sentence spans, and you do exact match, and they remove all but one. So if you're kind of paying attention, you realize that there's something kind of a bit strange about this because you're looking at 3 sentence spans, and if you find 2 documents with 3 sentence spans and remove all but one, that means you're just going to rip out 3 sentences from that document, which is a little bit strange because it breaks the coherence, but this is what they did. Okay, so that's exact deduplication. So how do we do near deduplication? So first of all, we have to define what approximate match means here. Okay, so to do that, we're going to define this called Jacquard similarity, which is a fairly standard notion. And Jacquard of 2 sets is basically the size of the intersection over the size of a union. Okay, so given these 2 sets, 1, 2, 3, 4, and 1, 2, 3, 5, when you compute Jacquard, you take the intersection, that's 1, 2, 3. You take the union, that's 1, 2, 3, 4, 5, and you divide, and the Jacquard is 0.6. Okay, so the Jacquard is a number between 0 and 1. 0 means that they're disjoint. 1 means that they're identical. Okay, so a fairly natural notion. And we're going to say that 2 documents are near duplicates if their Jacquard similarity is above some threshold, let's say 0.99. So now the question is, how do you find near duplicates in linear time? Okay, so fortunately, this is a solved algorithms question. And the answer is to use min hash. So, so the first step is to use min hash. That's not the final answer. So min hash is a random hash function so that the probability of a hash collision is exactly the Jacquard of A and B. So this is a very kind of nice property because hash functions, hashing is good for making things linear time. Jacquard is the metric that we want, and we're sort of connecting these 2 right now in expectation. So what's interesting is that normally you want hash functions to define hash functions so that everything is hashing to distinct elements are hashing to different things. You don't want collisions. But here you actually want collisions, not arbitrary collisions, but you want to control the collisions in a certain way to align with a similarity. So similar things you want to collide more than the disparate things. Okay, so the min hash is essentially you actually, let's see, maybe I will. Okay, so here's the min hash. It's fairly simple. You take a set, and you hash every element in that set, and you take the minimum element. Okay, so this might, if you're seeing this for the first time, it may seem a little bit strange. Why are you taking the min? You can take the max too. Doesn't really matter. It's just a way to break ties. So here's the picture that you should have in your mind. So okay, so if you have A, remember A contains 1, 2, 3, 4, and B contains 1, 2, 3, 5. So this is a characteristic matrix representation of these 2 sets, right? And so what the random hash function is doing is that it induces a permutation over the items. Okay, so it might be 4, 3, 1, 5, 2, or something else. And then you look at which item is first, according to this permutation, in A, and which item is first in B. So each item has the same probability of being first. Okay, so if the random hash function puts 1 first, then first in A will be equal to first in B. And if it's 2 first, then it's the same. If it's 3 first, it's also the same. But if the random permutation puts 4 first, then the first element in A is going to be different from the first element in B. And same with 5. Okay, so look at this representation. Basically, the random hash function says, elect one of these rows to be first. And then when the min is just telling me, the min equal of A equal to the min of B is basically telling me whether that row is the same. Okay, so that is the proof of why min hash, why this property holds, which is that you have a hash function in expectation over your random choice of hash functions, that the probability of collision is the similarity metric you want. Okay, so let's just check this in code. So I'm going to generate 100 different hash functions. Each hash function is given by a seed, and I just check whether the min hash is equal to min hash and the estimated Jacquard. So I'm going to just look at the number of the fraction of matches, and you get 0.6. Okay, and the key thing with the min hash is that I don't have to do the n squared thing. I can compute the min hash of A and the min hash of B and min hash of a different set, and I just look for collisions. Okay. Any questions so far about min hash? So now we can hash our items, but we're not done yet because a collision doesn't tell us the Jacquard is above some threshold, which is what we want. We want to find A and B such that Jacquard is greater than 0.99. All we've done is said, okay, well, if we got a collision, the probability of that collision of two things colliding is the Jacquard. But that's not really that useful by itself. It's stochastic, and I can't really get anything reliable here. So the next idea is this thing called locality-sensitive hashing, which essentially solves this problem. So this is a very classic idea in theoretical computer science, and it's quite nice. So the idea here is that we have A and B colliding with probability equal to Jacquard. Okay, so it is true that more similar items will collide more often, but it's very stochastic. Right? The variance is quite large here. So our goal is to have A and B collide if the Jacquard is greater than some threshold. So we, in some sense, have to sharpen these probabilities somehow. Like the probability can't just be literally equal to the Jacquard. So the solution is to use more hash functions. And these hash functions are going to be independent. So this part is, gets a bit technical, but we'll walk through it. So you break the n hash functions into B bands of R hash function. So if you have 12 hash functions, you have 3 bands. Each band has R4 hash functions. Okay, so there's a band here, H1 through H4. Here's a second band, H5 through H8. Third band, H9 through H12. Okay, and then so what we're going to try to do. So each hash function gives us either collision or not collision. Okay, and so every hash function there's a probability of colliding. So the key here is that we want to say compute the probability that A and B collide. We say that A and B collide if for some band, all of its hash functions return the same value. Okay, so if H5 and H6 and H7 and H8 all return the same value, so, sorry, if HA of A equals H5 of A equals H5 of B, and H6 of A equals H6 of B, and so on, that means this band is triggered, and then I would say they collide. Or if this band, if all of these say agree, then I say it's collision, or these two. But you don't have to have all the hash functions return the same value. Okay, so there's sort of this and or structure here that is doing the lifting here, and we'll see why this works. So, so now let's say you have a particular Jacquard of A and B. What is the probability that A and B collide according to this definition? Okay, so we can calculate this. So let's say that this Jacquard similarity is 0.8. Okay, and we have 5 bands, and each band has 10 hash functions. So then we can say, what is the probability of a fixed band matching? So that's 0.8 to the R, because each band has R hash functions. So the probability that they all have to match is 0.8 to the R. Okay, so the probability of a fixed band matching is generally quite low. It's exponential in R. Okay, and then now the probability of collision is the probability that some band matches. And that's going to be the probability of 1 minus the probability of, so this is the probability of a band not matching. And this, if you raise it to the B, there's B bands. This is a probability that all of them don't match. And then 1 minus that is the probability that some match. Okay, so the probability of collision is 0.4. And you're expected to be higher because you're given B tries to get a match. Okay. So if you plot this, this is what it looks like. Okay, so you have on the x-axis the similarity here, and we were looking at 0.8, and you look at the probability of a collision here. So we would expect that if the similarity is 0, then it should be 0. If it's 1, it's 1. But notice that this is kind of interesting S-shaped, which is nice because this is what we wanted to sharpen. We wanted to basically say if the similarity is below some threshold, then we want the probability to match to be as low as possible. And if the similarity is above some threshold, we want it to be as high as possible. So we're trying to get this to be like a phase transition. Okay, and if you plot this function as a function of similarity, that's what you get. Okay, so oops. Okay, so let's just look at some examples. So let's concretely, we have similarity 0.7 to 0.98. Okay, and we're going to look at how B equals 10, R equals 10. So we look at the collision probability according to our definition, and we see that this gives us a range of 0.25 to 1. Okay, so if you were to set a threshold, this is not bad. We can set it here, and these with some probability will there's still false positives because even if these are below a threshold, let's say 0.9, these might still collide. But we can filter them out if we want. But the ones above are mostly kept. So what happens when you move, so increasing R? So remember, R is a number of hash functions within a bucket. So when you increase R, the threshold sharpens and moves the curve to the right. Everything becomes harder to match, right? Because you have more hash functions inside a bucket, it sharpens that exponent. So the probability you see here are kind of sharper here, and now everything moves to the right. And now it's fairly unlikely that if something has low Jacquard, you're going to match it. So before it was like 0.25, and now it's 0.008. Okay, so we're sharpening the probabilities. And then increasing B has the effect of moving the curve to the left. It makes it easier to match. B is the number of bands, and some band has to match. If you have more bands, then there's more chances of matching. So if you look at this, then before and after, so now we're making, before this 0.9 was only 0.72, and now it's 0.92. And of course, this also increases, but not by that much. Okay, so and you can drive these phase transitions to be as sharp as you want by increasing B and R. But of course, if you can increase B and R too much, then it can be more expensive. But okay, so let's look at a more real-world setting. So in this paper on deduplication, they had B 20 bands, and R is 450. So to give you an idea of the magnitude of these numbers. And in general, the phase transition happens at a threshold, which is 1 over B raised to the power of 1 over R. So if you want to find if you want to filter based on Jacquard greater than 0.9, then you basically have to set B and R such that this is 0.9. And then by changing B and R, you can make that phase transition sharper. Okay, so remember, the probability that a fixed band matches is 1 over B. If you are at this threshold, then the probability that A and B collide is approximately, it's a constant. So the probability of collision is 0.64. Okay, and this makes sense. So basically, if you have a phase transition, the sort of center of that phase transition is like 0.64, and everything below it should go to 0 as B and R increases, and everything above it should go to 1 as B and R increases. Okay, any questions about LSH? So this method is called min-hash LSH because LSH really works for any hash functions. For deduplication language model processing, we're using the min-hash, which approximates Jacquard, and so that basically is the one you should use here. Okay, questions about dedupe? So one note about dedupe is that there's often, as we'll see, data sets that are coming in, and sometimes the duplication will happen within a data set, but you actually have to do duplication across your entire data set because often data sets can be redundant. So sometimes that's not done, but it should be. Okay, let's go on to the next topic, which is data mixing. Okay, so far we've transformed our data from really raw HTML or PDFs into text. We filtered for high quality. We deduped, so we have a smaller set of high quality documents, and this generally happens for a given data source. But language models are trained on multiple data sources. So in Marin, currently, this this website tracks the different data sources that the next model will be trained on, and you can see that there's a bunch of things. There's some Nebatron, there's Find PDFs, which we talked about. There's some institutional books, and some code and all these things. Okay, so you have all these different sources, and the question is, how do you combine these? So if you look at an older paper, the pile, this is the set of sources that they had at that time, and they essentially assign a particular weight to each component. So basically you have a distribution of resources. Okay? And so where does that weight come from? So more, just cut and dry, let's say you have 3 sources, you want to find a data mixture, and a data mixture is just a distribution over your sources. Okay, so if you're just thinking about this problem from first principles, well, not from first principles, but like just from what you might do. Vibes, which is I guess the opposite of first principles, is you just manually set it based on some intuition, which is more often than you might think what people do, right? So I think this is definitely fairly vibes based, and even more recent papers, you just look at it. Maybe you use some method and then you just like tweak things. You can also do uniform sampling, which is you just put a uniform distribution over your sources, and you sample every chunk you get. You just sample a source. You can also do proportional mixing, which is that you sample proportional to the number of tokens in a source. So if you have a data set with more tokens, then you put a higher weight. So this is also generally a rational thing to do, but you might worry that if you have a huge low quality data set, that's going to eat up a lot of your tokens. So this doesn't seem quite optimal either. So intuitively, you should upweight your higher quality sources. Okay, but there's 2 things that are important to keep in mind. One is that you do want to ensure some diversity, right? So often sources are incomparable. For literature, code, and papers, you can't really say that this paper is higher quality than this code because they're just incomparable objects maybe. And if you want your language model to do well, you don't want to just put all your mass on just papers. The second thing, which we'll talk a bit more about, is each source is actually finite. So if you put too much weight on a small source, then you essentially run out of that source, and you need to just epoch over it, meaning that you keep on training on literally the same tokens. And this is going to be bad for reasons we'll see. Okay, so let's try to unpack this a little bit more concretely, this last point. So imagine you just have 2 sources. A low quality source, you have 10 trillion tokens, and you have a high quality source that has 10 billion tokens. Generally, high quality sources are smaller. Okay, so if you just do a naive data mixture, let's just do uniform. So half on high, half on low. And I'm going to train for 1 trillion tokens. So when I say train for 1 trillion tokens, that doesn't mean unique tokens. That just means train for that many steps divided by batch size, essentially, or times batch size. Okay, so then let's look at this, which is the number of times a particular element in the low quality data set was trained on. So that's the number of epochs a particular data point was trained on. So P low times the train tokens is the number of times I want to request tokens from this low quality source, and divided by the total number of low quality sources. So this is less than 1. So basically that means 5% of the tokens in this low quality data set I'm even going to touch and train on once. And then if you look at high quality, you'll see that the number of epochs is 50, right? Because I only have 10 billion tokens here. And if I'm half-half, that means 500 billion tokens. I need to train on 500 billion tokens of high-quality data. But I don't have 500 billion tokens of data, so I have to repeat each data point 50 times. Okay, so this is actually really important, and some big model runs have kind of messed this up. Is that you can't just naively look at the data sets and define a distribution and then you sample, because if you just look at the quality, if you look at the data, you're sort of missing how many data points are there. Okay, does this make sense? Maybe pause for questions. This is a kind of important point. Okay, so yeah.
So that it takes a time when you talks as like very low quality. I guess like does it like why do we need 50 bucks in the first place? Like doesn't it achieve comparable performance at a level that's way fewer?
Yeah. So the question is, why do you need 50 epochs? And I guess the point is that you don't need 50 epochs. Worst case, it's wasting compute. Best case is wasting compute, and worst case, you're overfitting. But 50, the reason it's 50 is that if you just go in and you define this data mixture, then you're going to be ending up doing 50 epochs without realizing it unless you're paying close attention. So this is basically, the lesson is like, look at how many epochs you're actually doing on your data. Yeah?
How do the mixtures get expressed during training? Like, so when you switch every step, do you train like steps of 10, saying, oh, I want to do 10 blocks of Python code, 10 of C? Because I feel like, is there also any intuition between what decisions are made there?
Yeah, good question. So the question is like how, when you train, how do the mixtures get kind of realized? And so in general, you sample, so you want to fill a batch, right? So you can sample essentially for each element which mixture component it comes from. And you fill up a batch with sequences from that mixture component. Usually every sequence comes from one mixture component. You're not sampling like per token.
I guess so each batch should be mixed. So I guess the mixture assumptions are at the batch level, and then you train for that. It's not like, oh, there's one step is trained, one step is after.
Yeah, in general, you want to reduce variance. You want to train from multiple. A batch should have some mixture. Yeah. Okay, so this idea, this problem has been noticed, quite a long time ago. And so in this paper, they introduced Unimax, and in that case, it was they were training multilingual models. And it was like very clear that some languages were very low resource, so you had to do something about this. So in this paper, they noticed that before, some works would essentially take the proportional mixing and raise it to some power to kind of flatten it out, the distribution. But the idea in this paper is that let's be a bit more kind of explicit about that. Let's sample the sources uniformly, but with a hard cap on the number of epochs. Okay, so this is the key idea here, is that you say, I'm only going to take 20 epochs over a particular data source. So if you've done that, then too bad. You don't get any more tokens. You move on to the next thing. So this is sort of like a safety net in some sense. So in particular, if you look at the probability assigned to a source times the number of training tokens, that should be less or equal to the cap. Okay, and there's a simple procedure for actually just determining the mixture subject to this constraint. Okay, so let's switch gears a little bit and talk about how we define the mixture in the first place, right? Because if you have 50 sources, there's 50 numbers you have to fill. And we noticed that proportional mixing isn't really enough. Maybe you can try to estimate some quality metric, and then you can sample proportional to that. But that is also heuristic. So the most principled methods and most kind of easiest to understand like what's happening is these regression-based mixing methods, so regmix, oldmix, and other papers like this. And the idea here is relatively simple. So first, let's say you're trying to train a large-scale model. So you go to a small scale, let's say let's say 300 million parameters, and you try different data mixtures. So let's say you have 3 components, you try different mixtures, and then you train these small models. So you train a swarm of small models. Each model gives you a loss on some target metric. It could be some downstream evals, it could be perplexity, whatever you want. Okay, so you use these data points to basically fit a regression where the regression model maps these inputs, which is the data mixture weights, to the loss. Okay? So now you have basically a very cheap model that tells you, if I were to train on this mixture, what loss would I get? Then you can essentially optimize that data mixture. Optimize that function for the optimal data mixture. And then that is the data mixture you use to train the large-scale model. Okay, so that's the kind of the simple procedure. And you notice some kind of similarities with scaling laws, where you're trying to do some cheap computations to figure out some answers and then scale up. Okay, so there's a few design decisions here. One is, what are the mixtures that you're trying out here? You need a distribution over distributions here. So often people use some Dirichlet distribution. You also have to define the regression method. People have tried linear models or boosted decision trees. You have to figure out the target here. Often this is based on downstream evals, but you have to be very careful not to overfit, right? Because we're doing pre-training, and then supposedly pre-training is supposed to be training this general purpose model, and we're not trying to fit some downstream evals. And if you're not careful, for example, if you have a bunch of code evals, then, well, guess what? You're going to upweight all the code data. That's not rocket science. And if you then go and you say, I want to generate some poetry, you might realize that you've overfit. So you have to be very careful about that. So proportional mixing and uniform mixing don't have this problem because you're not looking, there's no downstream evals. And the final thing is that how much of a difference between small and large scale is there? And this is a cost and accuracy trade-off. Of course, if you train really, really small models, this might not be representative. But if you train large models to do this, there's no point in doing any of this. You just train, and you're basically doing hyperparameter tuning at the largest scale, which is too expensive. So this omics paper actually does has this nice table which shows you for a number of different methods that all fall into this kind of framework. The size of the proxy models, they're generally fairly, tens or tens of millions of parameters. How many, points do you sample, mixtures do you sample? M here being the number of parameters in your mixture, the number of domains rather. And you can use Dirichlet, you can use exponential, and then the regression model, you can fit a log linear model, which tends to work pretty well. And then you can use different ways to solve this optimization problem. Okay, so there's sort of two leaps of faith here that you just have to be very careful of, is that the regression model was trained on a bunch of these small proxy runs. And you're optimizing this. So the hope is that the minimizer, your optimal data mixture, the regression model is still accurate. And this is a little bit kind of, you have to be very careful because if you, let's say, sample a random mixture, you'll probably be fine because of classic generalization. You sample a mixture, and you fit a function, it should be able to predict in distribution. But when you're optimizing, you're essentially trying to go to potentially the extremes where you might not have as much coverage. So that's one thing to be careful of. And the other thing is that optimal data mixtures, you just hope that they transfer for small scale to large scale. And this, in general, it seems like at least at the scales that the open community works with, tends to be true or not blatantly false. But clearly there are scale-dependent effects. If you just think about the previous slide when we were talking about filtering, if you're training for many more tokens, then probably low-quality data is okay. So clearly the optimum is not the same, but you just kind of hope for the best here. Okay, so hold on. There's one scale-dependent effect that we already talked about, and we need to address here, which is that imagine, so we have a lot of low-quality data, 10 trillion tokens, 10 billion tokens of high-quality data. And if we train a small model on low token counts, remember what happens is that you might, this is a made-up example, but you might put a lot of mass on your high-quality data. Because if low token counts, you're not epoching, so it's like, oh, wow, Wikipedia is so great. Let's just train on Wikipedia. But if you then go and train your large mixture on this, large model on this mixture, then you're going to end up epoching a lot on this high-quality data and you'll overfit, and that's definitely bad. So one way to fix this, which is done in the omics, this omics paper, is you can just cap the number of epochs. Okay, so that is one solution. There's another solution here which goes by probably multiple names, but one name for it is simulated epoching. And the principle here is that make your small scale look like your large scale. This is kind of a general theme for the course. We saw it in kind of when Tatsu talked about mu-p. You parameterize your model so that your hyperparameters transfer. And so the kind of same principle applies here. And the problem with doing this kind of naive scaling is that at low, you can't be not epoching at small scale and then epoching at large scales, because then those are qualitatively different operations on your data set. So the way you would handle this is you downstream your sources proportionally. So if you have your small runs that were 10 billion tokens and your big run were 1 trillion tokens, then you have 1 in 100 kind of downsampling, and then you basically use the downsampled mixture. And so the idea is that if you have the downsampled data, then this solution is not going to look good, because you're not training on all. You don't get to just train on all Wikipedia. You're going to train on some minuscule fraction of the Wikipedia, and you'll realize, oh, actually, I'm going to be epoching a lot, and that's going to have really bad loss, which means that in the optimization, you're going to look for more balanced approaches. So you're kind of simulating the data scarcity that you would get in your high regime at low scale. Okay. So to summarize this section, the problem is how do you weight different sources? You have Wikipedia, you have your Common Crawl, you have your code, you have some math data that you scraped from somewhere. How do you balance them? Regression-based mixing is a nice framework, I think, to think about things. You you estimate a function form that maps your mixture weights to a loss at small scale, optimize, and then you generalize to large scale. And you just have to be very careful with this because of epoching and overfitting kind of issues, and you have to either use capped epoching or simulated epoching. So one lesson here is that if you're trying to optimize anything, you have to be very careful because you are in danger of optimizing the wrong thing. Okay, any questions about data mixing before we move on?
When you're downsampling, is there something as like too small that like you can't really generalize as well?
So the question is, if you're downsampling, is there a risk maybe you get too small of a data set? Yeah, absolutely. So I think, right, you might get into a case where you just have so few tokens. I think then what will happen is that your optimum will just put very small mass on that. And when you scale up, maybe you get the right set of tokens. So in principle, like, it should work out, but there might be like rounding errors where like you end up, instead of training once on this data set, you train like 0 times by accident. But you can sort of work around these by just like think you always train once on this data. Yeah. Okay, so yeah.
Within data mixing, do you ever, because like I guess these sources just happen to align with different topics, but do you ever take like a diverse data set and then try to do like data mixing within that?
Yeah. So the question is, what do you apply data mixing to? The like different domains or even within a data set? That's actually, I forgot to mention that, so I'm glad you brought it up. So in the Nemotron paper, they actually, and some of the OMO stuff as well, you basically think about, let's say I give you just common crawl, right? You can actually break this up. So you can group by domain. So the AI2 folks have this like web organizer, so you can group into topics. But you can also quality filter. So then you have this like 2-dimensional grid where you have domains and you have quality. And each of these cells is something that you would data mix. So that's one automatic way to determine the domains. And then on top of that, you add extra sources that people hand you. Okay, so I'm going to quickly go through post-training data here. So up until now, this is basically pre-training or maybe mid-training data. It's generally fairly task agnostic, except for the reg mix stuff where you're trying to minimize the loss, but still the data itself is still relatively task agnostic, and you're trying to develop basic skills. So when you look at post-training, a lot of the data becomes very kind of task dependent. And I'm not going to do a comprehensive review. I just want to point out some of interesting post-training data sets that have been recently released, in particular for coding, since that's of, I think, great interest these days. So the general recipe is you define a set of environments. In the case, think about code, which might be GitHub repos. You define a set of tasks or prompts, and then you collect responses from a strong model or teacher. So implicitly, at least in the open community, almost all the post-training data, that's most of it is synthetically generated. You can also replace strong model with a human, but that is slow and costs a lot of money. But if you're at the frontier and of, I guess a few years ago, you kind of had to go and pay a lot of people a lot of money to give you responses. And nowadays, even at the frontier, you can do sort of hybrid human AI things. But anyway, the point is that there's some teacher out there that's giving you responses. Okay, so a few kind of, I'm just going to talk to a few works here. So one is this works called Open Thoughts. And this idea here is, this came around, it was motivated by when O1 came out, and there was a lot of intention on reasoning, mostly for like math and science. How do we get really good post-training data sets for this? And they eventually came out with 1.2 million examples using this teacher model. So the steps are, first of all, there are a bunch of, so what are the environments and the tasks and questions? There are a lot of different sources that they drew from. There are human sources like Stack Exchange or Newman Math, and then there's like some synthetic sources as well. These are just a subset of the coding ones, but there's also more for math and chemistry. This is a big project that involved a lot of different contributions from many people. So you can see that there's, some of these are like coding exercises. Some of these are, more realistic things that show up on. I guess code golf is not realistic, but there are some more realistic examples here. So code review, this is probably more realistic. And they noticed they did a fairly comprehensive analysis of, given this data set, how do you generate responses? They show that having a few sources was actually good, rather than trying to do all sources. Sampling multiple generations is helpful, like 16. One thing that was interesting is that having better models aren't necessarily better teachers. So for example, QWQ 32B, which is now a very old and small model, was a better teacher than DeepSeek R1, which was at the time probably one of the strongest open models. They also found that basic answer filtering wasn't helpful. And so the entire pipeline looks something like this, where you have a bunch of these sources going in, and then you duplicate, you randomly sample, I guess this downsample the questions, and you generate multiple answers, and that gets into the final data set. So the 1.2 million is examples, but divided by 16 gives you the number of actual questions. Okay, so there's another. So that was for math and science and some code. I think more recently there's been a lot of interest in developing, in particular, agentic coding models. So not just a model that can just generate some code, but actually a model that can do software development. So this Smith paper had the idea of you're given a repository, you're using a language model to automatically generate tasks. So they have an agent that takes a repository and actually makes it usable for installing dependencies and so on. And then you generate tasks which are generally, you modify the code in some way, maybe introduce some bugs. And those get verified and you get task instances. So these are synthetic tasks, but you get 50K of them, which was actually, at the time, which was last year, quite large. So since then, there's been a bunch of other work which I'll mention. So there's this SWE-0 paper from NVIDIA, which had this kind of okay, I'll also talk about that. So this is a kind of an interesting idea where the observation was that unlike math, SWE tasks have just a lot of heavy dependencies. Most GitHub repos don't even run. And you have to install all these dependencies that are out of date, especially if you roll back to when a PR was. It's just kind of a mess. And this is just a nightmare. And so they were thinking about how can we actually get a data set that just on all the repos. And rather than having a repo-specific Docker image, they noticed that the models are actually good enough that they can solve a lot of these tasks without execution feedback. So if you look at some of these models, if you were allowing execution, you get like 80. If you don't allow execution, you get almost 70. So which is not bad for not being able to execute code. So somehow these models have some internal semantics of code. So they were able to generate 300,000 agent trajectories. All of these are real GitHub PRs, so they're realistic, unlike the Smith examples. They used the open hands scaffold and did some. There's a lot of details like how to prevent agent hacking. So normally you hand an agent this instruction, you explore, you test, you implement, and their 3.0 version was basically saying you cannot run Python code. You can only do like set and grep and all these like basic operations. Okay, so then they distilled from a big coding model and filtered because sometimes a coding model will ignore these instructions and still try to execute anyway. And then they showed that with this, they also had 13K agent trajectories that do require execution feedback. So they trained models where they first fine-tune on these 3.0 examples and then fine-tune again on these 3.0 examples. And they were able to, I guess the frontier is still pretty high up, but they were able to make some progress here. I'll quickly go through 3rebench was essentially another attempt to grab tons and tons of PRs. And all of these kind of look like get a bunch of GitHub repos, try to install the repo. Like most of them probably fail, try harder, and then you use a language model to give you the responses. So in this, this actually just came out today. So you can take the 3.0 idea and you can now scale up to 12 million agent trajectories. The nice benefit of 3.0 is that it's just it's very lightweight. Here they use the rebench tasks. So in this one, remember they were trying to get things to execute. They only got 32,000 of them to execute, and 120 of them didn't execute. So but 3.0 doesn't care. You can use all of them. This is a very small model because now this data set is quite large. And so, I think as you can see, the data sets are getting more and more sophisticated. You go from environment-free things like math to now coding, and now the coding data sets are growing quite a bit. But the general idea is that you have these prompts, which there's kind of trade-offs. You can have fully synthetic. You can have semi-synthetic, where you have a real environment, and synthetic tasks, where you can have real. And the responses generally are coming from just capable models, but they also need to be good teachers. Code environments are a pain, and there's a lot of filtering and other details, which we don't have time for. Okay, to summarize this lecture, we talked about filtering. So define what good looks like, and then train a lightweight classifier, go over your web crawl, and you can get a small subset that matches what you're looking for. Deduplication is important to avoid overfitting and saving flops. Mixing, try mixture at small scales, extrapolate to large scale. And then we looked at some post-training data. I will say that, though, that a lot of the data work can be very grungy. It's very domain-specific and requires looking at concrete examples to make these high-quality data sets. So this lecture is not really representative of what data work is like, but hopefully I've given you an idea of the data landscape out there. Okay, that will be it for today.